Okay, so getting started. So we're going to start today with, we're going to talk about some applications. There's a few interesting points in here. There's also a bunch of not math in here. There's some physics, primarily, of course. And just some sort of, random other little topics. So the focus here is going to be on the multivariable calculus. This is not a physics class. So I'm going to try to avoid turning this into me teaching physics, right? As much as is possible. Okay. All right. So we're going to start off with an idea called averaging. I think this is a pretty familiar idea. Y'all know how to average numbers. Here I've averaged 6 numbers. You add them up, you divide by 6. So there is another way to think about this. By the way, let me just check one thing real quick. Did I start the recording? Yeah, apparently I did. Okay. So different way to think about this. I kind of am only averaging 3 numbers, right? 4, 7, and 8. But I'm kind of double counting the 4, and I'm triple counting the 8, right? So it's like I want the 4 to count more, and I want the 8 to count more, even more, right? So one way to rewrite the algebra, of course, you'll notice, is this, which, of course, you can write with sigma notation like this. And what's nice about this is that it sort of documents this idea of what it means to double count something. Double counting the 4 means that it's going to count twice in the summation, and it's going to contribute 2 to the denominator. Or said differently, these 2's right here, like those 2's, like those WI's right there. Okay, and then likewise, what does it mean to triple count? Well, same deal. The 8 is added 3 times in the numerator, and it contributes 3 to the denominator. So the big idea then is that we can generalize the idea. Hang on. We can generalize the idea of averaging numbers while we double count, triple count, count arbitrary number of times, or even counting. Now that I don't have to think of this as, just literally an integer number of occurrences, these W's indicating what up here is how many times I've counted them in the average, these don't even have to be integers anymore because I've written it in sort of algebra. Right? So this is called a weighted average. If you are averaging the numbers in green, but you want some to count more than others according to certain weights in blue, that's the formula that does it, and it gives us what we call the weighted average. Now, the most immediate application of this for y'all is course grades in this class, right? Or can be largely computed by a weighted average. All the details, of course, are on the course webpage, class webpage, right? Some of that's course policy, some of it's section, class policy. So the example that I have here is not exactly quite consistent with the weights that we're going to be using. And of course, we only have 3 midterms, not 4 midterms, and we do have a final, so everything's a little bit different. But this calculation is representative of pretty much how you're going to compute your final course weighted average, which will determine your course grade. Okay, so the big idea here is, Bob's got certain grades that he's gotten in certain exams, and these are those grades, and they're going to go in spots like that per the formula, and the weights are 20, 20, 20, and 40. Again, for this, whatever hypothetical class he's taking. And so this is how you compute Bob's weighted average by this formula, the arithmetic of which turns out like this, and Bob gets a B in the class, right? Because this would be in the bin where 3.0 is the center of that bin. Okay. So anyway, this is a nice example of weighted average, and it's also hopefully an assistance to y'all in seeing exactly how grades are going to work in this course. A quick reminder, slightly off topic. If you have any questions about how course grades are computed in this course, just come talk to me. I'll be very happy to clarify. I don't want anyone to be confused about exactly how that's going to work. It's all extremely formulaic, and just come talk to me and I'll be happy to clarify. Okay, so here's the thing. We can kind of steal that idea of a weighted average, and we can average the values of a function. So you have some function, real valued function, right? Well, those values, you can ask, what is the average of all of those values? And typically when you're talking about the average value of a function, you use size in the domain as the weights. So dx, if you break up the entire interval from a to b into a bunch of little pieces, each one of those pieces has a certain amount of size in the domain, which we're going to think of as dx. So what we have here then is a weighted average based on the idea of a weighted average, and this is what we call the average value of a function. Okay. So, easy example, if you want to know what's the average value of sine x between 0 and pi, you plug into this formula, easy integral, answer, and there you go. All right. Okay, you can do this in a multivariable setting as well. Here I have a real valued now still. We're still looking at real valued function. But this is a function defined on a two-dimensional domain, right? And same basic idea. We use size in the domain as the weights while we're adding up and, averaging in the usual way, sort of, the values of the function. And likewise, then, the average value of a function from R2 to R1 is this formula right here. And of course, it's easy to notice that this is literally just talking about the area of your domain. And so that streamlines things just a little bit. Okay. So an example of this. Again, it's just a matter of plugging in. If you're interested in this function, x squared, you want that to be your f of x. That's what you want to find the average value of, specifically over the unit disk. Okay, which means we're going to integrate on the unit disk, right? That's going to be our dA. That's going to be the thing whose area we have to divide by, like so. Right? Yeah.
We always take r as positive, right?
Do what now?
Do we always take r as positive, like
R.
the bounds?
What,
like 0 to 1, it would be like 0 to minus 1.
Oh, I'm sorry. Yeah, so you're talking about this r down here.
Yes.
Yeah, so when you use polar coordinates, if you want to be able to avoid absolute values in your stretching factor, yeah, always choose r to be positive. Don't ever choose negative r's. Yeah, that's right. Yeah, exactly. Conveniently, usually the easy choices. Yeah, that's right. Okay. So, so we have here an integral that computes the average value for us. And how are we going to compute that integral? And again, don't forget you have a toolbox full of tools. Pick your favorite, pick the one that's most appropriate to the circumstance. And here, especially given that my domain is the unit, the unit disk, I think polar coordinates is the smart move, right? That'd be my favorite tool to choose. I mean, I guess we could do this in rectangular coordinates. Who needs it? That'd be square roots and difficulty, and oh my gosh, I don't want any part of that. So this works out very nicely. dA is RD theta, right? Don't forget that stretching factor, tremendously important, super easy to forget, right? Always written down all at once at the same time as you're writing your differentials. And the integral ends up being a pretty straightforward integral. The answer is 1/4. Kind of interesting. Everybody happy? Okay, so turns out there's an application of taking an average value of a function, and that is when you want to make sense out of the idea of a center of mass. Turns out it's very conveniently represented as the weighted average of position. Nice and crisp, nice and simple. And let me just show you how literally and conveniently this works out. This, weighted average of position. Well, this is how you compute a weighted average. That's, a finite number of masses, just two masses here. We don't need to write sigmas or integrals or anything like that. Just there's two masses, and that's our formula for a weighted average. Obviously, we're going to use the weights, the masses, I guess I should say. We're going to use those masses as the weights. And we're taking a weighted average of position. So position, where they are on the x-axis, these given x1 and x2, those are what we're doing a weighted average of. And when you compute that out, what you will get is a point like this. You'll notice that the larger weight of M2 kind of pulls the weighted average closer to M2 because it counts more, because it has more mass and therefore has more weight in the average. Now, a different way to think about this, and this is a physics thing, this is a digression, it's not critical, but you might find this useful in some future course. If you were to think about your situation of having two masses as being sort of connected by a massless, imagine a little piece of balsa wood, right? A little very, ignorable amount of mass between, let's say, two, heavy pieces of, metal, something, iron, the little weights. And you want to know, where would you put your finger to make it balance? It turns out that that is another take on the weighted average. It's the balance point. And the idea is that the torque adds up to 0. If you look at the amount of torque that this mass creates by gravity pulling it down, that's going to create what you might call a clockwise torque. But on the other hand, there's also this little piece of mass. Now, it's less mass, but it has a longer sort of radial arm for the downward force to create torque with. And it turns out those torques are exactly balanced. They're exact opposites of each other. And exactly the weighted average of position, the center of mass, thought of as a weighted average, is what makes the total torque add up to 0. Now, this is easily checked. All you got to do is, write down x bar by this formula, compute literally the amount of torque on each side, and you'll find that they're the same with a minus sign. So, kind of cool. Okay, again, a little very quick physics diversion. Okay, taking that same idea, weighted average of position. This then is how you generalize that to higher dimensions, right? If you have not just masses distributed across a single axis, but masses distributed, let's say, in space, and you want to find the center of mass of that three-dimensional distribution of mass. Same basic idea, still a weighted average, still using masses as the weights, and with that doing a weighted average of position. And again, this streamlines pretty nicely. That, of course, is just the total mass. Let's go ahead and streamline that. And here's what's weird and a little unsettling, looking at this integral right here. That integral has a feature that we've never seen before. The integrand's a vector. Can you do that? Is that a thing, right? Could you do an integral where your integrand is a vector? Does that make sense? What does that even mean? There's some natural questions to think about. The good news is it's really not a problem at all. Because what I'm going to do with that integrand, well, I'm going to multiply by scalars, dm. How do you multiply a vector times a scalar? Well, one coordinate at a time. Then I'm going to be adding these things to each other. How do we add vectors? Well, one coordinate at a time, right, independently of each other. And then lastly, how do we scale a vector? Well, again, one coordinate at a time, independently of each other. So the beautiful simplification, very convenient punchline is the way you compute this integral is just one coordinate at a time. It's exactly what you would hope, exactly what you would probably guess, for lack of better ideas. Also happens to be exactly right. Yeah.
So then we'll sum up all of the integrals?
No. The answer is a vector.
Yeah,
Right.
So the answer is a vector.
The answer is a vector. That's right. So all the positions are vectors, and so the weighted average of those positions is also a vector. And what you compute one coordinate at a time
A vector.
are the coordinates of a
The
vector.
vector.
Yep.
Okay.
That's right. So that is a vector. Absolutely. All right. So let's see an example of this in action. Let's see here. I should give myself some more space. I'm going to try to get all this onto the screen at once here. So we are going to look at the upper half disk like so. And I'm going to imagine that I have mass distributed through that upper half disk, and a couple of relevant details. The radius is some value a, and I'm going to say that the mass is distributed uniformly, and in particular I'm going to say the density is 1, just to kind of keep things simple as a first example. How do we compute the location of the center of mass? And step 1 is to recognize that, look, we're going to be doing one coordinate at a time. Like so, there's going to be the first coordinate. Now I've set up this half disk in the xy plane, so it's not going to be x1, x2, x3, etc. It's going to be, my two coordinates are x and y. So there's going to be the x coordinate of my center of mass, and then here is the y coordinate of my center of mass. Let's just plug it in. Everybody on board so far? A few things to say about how to compute this. Okay. All right, well, how do we compute these things? And again, toolbox full of tools, so kind of, compute it by whatever means you think is going to be most convenient. I do think it's very valuable to note. Let's see if I can get this to, there we go. This integral right here, notice it did not announce itself as, hey, by the way, this is susceptible to a symmetry argument. It didn't, right? There was a formula. We wrote down the formula. No clue, no tip-off that this is susceptible to a symmetry argument. But it is, right? So this integral is 0. You can argue that by a symmetry argument. Make sure that you can fill in those details. This is a fantastic little example. And the big point that I want to make right here is don't wait for these arguments to announce themselves to you, right? Always be on the lookout. And my own little personal procedure on this is anytime I do an integral, I kind of have to draw the domain anyway, right? You got to have a picture of the domain to make whatever slicing argument you're going to make. And I just always look at my domain every single time, and I ask myself, hey, I wonder, wouldn't it be awesome if there was a symmetry to that domain? Then I could possibly consider an oddness of the integrand, and hey, this might, who knows, we might get lucky here. And in this case, when you think about it, it really does kind of leap off the page that this domain is symmetric over the y-axis, right? And reflecting over the y-axis looks like that. Write down a formula. Ask yourself whether x is odd, and indeed it is. Symmetric domain, odd integrand, that integral is 0 by symmetry. Again, make sure to think through the details. Make sure you're good with that argument. Make sure you always stay vigilant, right? Always on the lookout for possible good fortune like that. Yes?
Why, when we just change from dx dy to dy dx, the bounds of, let's say the radius, because I assume dx dy y is from 0 to a, so why would it be minus a to a and not 0 to a when we switch them?
So these are x bounds,
Yeah.
right? And when you do your x slices look like this, and they start there and end there. Yeah.
And the y. But
Yeah,
wouldn't
so
the y also?
This will be an after class thing. Yeah,
Okay.
yeah. Okay. So here's the two different breakdowns that you get for if you looking at the second integral here, looking at the y coordinate of the center of mass, and you think through the slicing process, right? So that's old material. This is the right answer. Make sure you can get the right answers. Come talk to me otherwise. what I want to talk about is how you should decide between these two options of which one to compute. Which one to take a deep breath and plow forward on. I've given you all a couple of rules. Those couple of rules give you what I'm going to call the best answer kind of 95% of the time, most of the time. Don't slice through corners. Try, if possible, to solve for whichever variable is going to be easier to solve for. And neither one of those considerations really helps us here. Right? We don't slice through corners in either direction that matter anyway. And this is a circle. X and Y are both equally convenient to solve for. So which one should I do? So in a few situations, the following little insight can help sometimes. And I'm sad to report, you kind of do have to have both of the integrals written down for this to work. So, don't go all in on one. If you feel like there's no particular reason to prefer one over the other, don't go all in until you've at least thought through what they both look like, and then watch out for the following, and that is this right here. Right? In this second integral, my very first antiderivative is going to make y squared be the relevant factor in the antiderivative. That squaring is going to make the square root disappear when you plug it in. All the integrals work out super easy. So that's awesome. Right? Whereas, on the other hand, because the order of the differentials is different here, there is no y squared that gets plugged in. You're looking at x antiderivatives. You're going to end up with y times the square root of a squared minus y squared, and like a 2 or something. Not that convenient. It just, the algebra just doesn't work out as well. I do not know how to see this coming without actually writing down the details and then just taking a careful look at it. So you don't have to literally compute both of them, right? That would defeat the purpose of trying to decide. But if you just look at the bounds and then think, sometimes something lucky like this will happen. Okay. All right. How we doing? Okay. All right. So this is a physics thing, and it's a very cool physics thing. And if you're engineering major, you're going to take a physics class in mechanics. Moment of inertia is a big deal. Look, the world is full of circles. The world is full of things that are rotating. Moment of inertia is a fundamental physics idea for understanding how things rotate and what is the corresponding amount of energy. Right? It's a very big deal. But this isn't a physics class. So what I'm going to talk about here is just kind of the bare bones. The idea is we have some axis, and there is some sort of a rotation around that axis. And you can write relationships between the speed and what we call the angular speed. Details y'all can think through on your own there. But the idea of angular speed is that it's a ripoff of the idea of speed. Speed is distance, linear measurement, distance per unit time. Angular speed is angle. A nonlinear measurement, right? An angular measurement, angle per unit time. Totally analogous, just angle instead of distance. So angular speed is a natural term. Sometimes they call this angular velocity. I feel like velocity suggests a vector. I try to avoid that term, but I do fall into bad habits sometimes. Okay, so there is that idea. And if you want to compute the kinetic energy, there's no problem, really. If you just have a single point mass, look, it's moving with some speed, and we have a formula for kinetic energy. It's 1/2 mv squared, right? Old news. Y'all don't need me for that. Here's where things get a little sticky. What if we had some big lump? Great big lump. Like this. So like maybe I've got some big thing and I'm holding it in my hand and I'm spinning it around like that, just around and around and around. How much kinetic energy does the lump have? And the problem is that if you look at a little piece of mass here, and then you look at another little piece of mass here, in one rotation, however long it takes me to do one rotation, the purple piece of mass only travels that distance, while the orange piece of mass travels a much greater distance in the same amount of time, which means it's moving faster, which means the two speeds are different, and so 1/2 mv squared, right? What do you mean by speed if the speed varies over the object in question? You just can't make any sense out of that. And so this is a hard problem. Everybody on board with the hiccup? Right? Okay. So, again, I'm going to try to avoid getting into the weeds on this. Y'all can look through this at your leisure if you're interested. Here's the big multivariable calculus idea. Step 1, energy is an accumulating quantity. Now, I'm just going to make a physical appeal here. If you have a bunch of mass, if you were to chop it up into little pieces, while it's rotating, it's the same total amount of energy, right? So the whole is the sum of the parts. Pretty believable, I think. And then on each little piece, because it's a little piece, all the mass in each little piece is moving the same velocity, and then on that little piece, the energy on each little piece, 1/2 mv squared. Sure, no problem. So effectively then, this problem can be broken down with a double integral, and then details, read the details if you're interested. That's all kind of just keeping track of the variables, etc. So here's the nice little punchline. Again, we were interested in computing kinetic energy. You can write the result as a formula that structurally, at least, looks a lot like that formula. It's 1/2 something times something squared, just like the linear formula for kinetic energy, right? And then furthermore, you look at this part of it. Remember, that's angular speed. I think it's reasonable to call that is kind of like linear speed. It's just in an angular sense instead of the linear sense. So this is an angular analog of speed. So let's count the analogies here. We have an angular analog of speed, right, in a formula that's totally analogous. And so doesn't it seem like a reasonable claim that this thing right here, whatever that is, and that was just a placeholder for this expression right here, that very reasonably should be thought of as an angular analog of mass. And this is my favorite way to think about moment of inertia. It's an angular analog of mass when it comes to computing kinetic energy. So the common notation is to call it I for inertia, I guess. And here's the formula. You want to make sure to memorize that formula, triple integral r squared dm. Actually, more generally, just integral r squared dm with the understanding that that integral is appropriate to whatever your shape of your solid, or whatever the shape of your mass is. And if it's 3-dimensional, then triple integral. If it's a 2-dimensional distribution of mass, double integral. Whatever. So integral r squared dm. Very general. And again, the term moment of inertia. So this is why we care about this expression. Now, for our Math219 purposes, here's what you really need to make sure you know, and that is moment of inertia is computed by that formula. That's the Math219 punchline, just integral r squared dm. All right, now there's a little subtlety here. Let's talk about the r. There's that r in the equation. You come back up here to our setup, you notice r is the distance from wherever I might happen to be, whatever little piece of mass I'm looking at, distance to the axis of rotation. And notice I deliberately drew this picture with my axis not being vertical. There's a lot of rotations that happen in the real world that are not around a perfectly vertical axis, right? Wheels of a car, by the way, right? Yeah, horizontal axis, not a vertical axis. By the way, if you are interested in mechanical engineering, and if you're interested in designing a car and maximizing fuel efficiency, and you want to think about how much energy does it take to get the car rolling, well, there's the question of the linear kinetic energy, and there's also the question of the wheels. The wheels have a rotational kinetic energy, and you got to account for that too. Right? And so that's actually a pretty significant example of why you need to understand moment of inertia, because you want your wheels, in some sense, to have as little moment of inertia as possible, right? Because you want that kinetic energy as low as possible. Okay. All right. Okay, so yeah, again, the point is R, not necessarily your cylindrical coordinate R. There's only so many letters in the alphabet. R is one of the ones that gets used a lot, but there's no way around it. We're going to duplicate usage of letters sometimes. This is one of those times. So you always have to kind of think through, appropriate to the situation, what your R is. It is always distance from the axis to whatever point you're looking at, x, y, z. In this case here, that distance happens to be the cylindrical coordinate R. How nice. You get lucky sometimes. Convenient. But if you had a different axis, let's say that line right there, parallel to the x-axis, this value y, this value z. I mean, the distance to that line is just a different formula. So the punchline here, you cannot memorize a single formula that will always tell you what your R is. The formula for R depends on the nature of your line. And so I strongly encourage you, again, don't memorize a single formula. Don't memorize a menu of, a finite number of possibilities, right? Finite number of cases. For two reasons. First of all, you can't that's just not going to generalize, right? There's too many cases to possibly entertain. And second of all, you will forget. Whatever it is that you memorize, you will forget that over time. It's too many formulas. So I would suggest every single time you do this, draw the line, draw a point x, comma, y, comma, z, and then just look at the geometry and compute that distance. Yes?
Wouldn't that technically be the same formula, but with b and c on the left being 0?
No, because this is y and z, that's x and y.
But if we...
Yeah, it's different.
Okay.
Does that make sense?
Yes,
right?
But so B and C here are like is like the center.
B and C is where those are the y and z coordinates of the line in question. Yeah, yeah, but there's no getting around the fact that this formula doesn't have a z in it, and this one does. You see, that's really kind of the bigger point. Yeah, right. Yeah, so there's too many different cases. You can't memorize all of them. Not a good plan. Okay, so let's see an example. We are looking here at this region over which mass is distributed according to this given density function. And we're going to imagine that is rotating around the x-axis. So this looks like a two-dimensional problem, but it isn't really. It's kind of a three-dimensional problem in the sense that as this area rotates around that axis, it's going to rotate through the third dimension, right? All right, so how do we add this up? Well, we're going to use our usual formula. That moment of inertia is integral r squared dm. This is a two-dimensional region, so it's a double integral. We add up over the region where the mass is. Let's see here, integral r squared dm. We got to. Let's think about the dm. Well, mass is density times area, and density is given right here. Density is 2 plus cosine x. So that's how the dm simplifies. Everybody happy? Everybody good? Yeah.
Just a quick question. Which is the y squared?
Oh, yeah, I'm coming to that. Yeah. Yeah. Right. So, but on the DM, is everybody happy on that part? Yeah. Okay. So, so where did the y come from? Well, I've got to entertain this question of what is this r? Right? The r from our original formula. Remember, it's different for every example. It's distance to the axis of rotation. Our axis of rotation is the x-axis. We're going around the x-axis. And, well, distance then, there's the picture. If I'm at some point x comma y in this two-dimensional region, what is the distance to the x-axis? Is y. The geometry here is extremely convenient, right, as it turns out in this particular case. And so that r is y. Is that cool? Yeah. Anybody else? Okay. All right. So and then of course, we're doing the integral. Doing the integral over this domain, which is this thing, and you got to slice that up, and the range of values of x and y, as I've, in the order that I've chosen to slice it here, which by the way I think is a good choice, how to slice this. We don't want to have arc sign in our question, right, in our work. Now I've got a double integral and plug and chug. I will point out, you've noticed that I've kind of started you on the calculation here. This inside integral turns out to be this, and that leaves you now with an outside integral that is got maybe some little slightly tricky single variable calculus there. And so let me just remind you, this is the kind of stuff that we do expect that you got to be good with this kind of stuff. You got to get that single variable calculus back up and running to where you can handle stuff like this. So just make sure to remember there are some tricky little cases. You just need to go back and remind yourself what's the trick with these annoying trig integrals of various sorts that come up, and just remember those little tricks. They're just tricks. Okay. All right. Okay. Is everybody happy? Yes.
Can you just quickly draw one of the? Is it dy slices doing?
The what now?
Like draw one of the dy slices.
So maybe what you mean is a dx slice. So x slices kind of look like this, right? And they go from 0 to pi.
Oh, okay, yeah.
You see what I'm saying, right? And then for a given single value of x, then I've got a slice that looks like that, and y starts at 0 and ends up here at y equals sine x. Yeah. All right. Okay. So, guess what? That does it for Chapter 5. Now, of course, we've got 11 minutes left for today. We are going to move into Chapter 6. This is an opportune time to remind y'all, I'm sure you haven't forgotten, but we do have an exam on Friday, right? So just a reminder, the stuff, remember the class schedule has all the details of what's fair game for when and et cetera. And so what we're doing today, all the stuff we're doing today, not fair game for Friday's exam, right? But just a reminder as well, exam 3 is actually not that far from now. And the end of the semester is kind of coming up here, right? Where November is like coming up in a couple of days, right? Anyway, for your consideration. Okay, so starting in Chapter 6. Every integral we've seen so far, and we've seen 3 of them, are what I'm going to call dimensionally convenient. Single variable integrals are one-dimensional domains in a one-dimensional world. Double integrals are a two-dimensional domain, but they're always in a two-dimensional world. Triple integrals, three-dimensional domain in a three-dimensional world. They're always kind of, in some sense, in the space that they most conveniently, I don't want to say they belong in, right, but that they're most conveniently understood in. And the problem is that is not representative of reality in a lot of cases. So, for example, if you have a curve like so, right, in the XY plane, like this curve is an intrinsically one-dimensional thing. It has a length. The word area doesn't make any sense for this curve. There is no such thing as area. I mean, it's zero, right? But I mean, area is not a useful concept to describe this line, this curve. But it lives in a two-dimensional world where area does make sense. So this is strange, right? We do not have a pre-existing notion of integral that makes sense on this domain. And yet, it is perfectly reasonable that we might conceivably want to add stuff up over a curve, right? I did an example one time in my personal life. I had to shovel a driveway. There was a bunch of snow. It was a lot of work. And I wanted credit for how much effort I had put in. I wanted to be able to say, I shoveled 10,000 pounds of snow. Or something like that. I wanted to know what the number was, right? I felt like it was going to be something to brag about, and I wanted to be able to brag about it. So how do you calculate how much snow there is on a curvy driveway? Well, big surprise, you take the driveway and you chop it into little pieces like this, and you find easy formulas to compute how much snow is on each little piece, and then you add up over the entire curve. So chop it up, add it up. The whole is the sum of the parts type arguments that we do so much in this class. In fact, every integral really is an argument that the whole is the sum of the parts. Naturally apply in weird domains like this one that are, dimensionally awkward. They live in a world that's higher dimension than they themselves actually are. Does that make sense to everybody? Okay. So, what are we going to do about this? Well, good news. It's the same basic idea. On any little piece, I'm going to be arguing a pretty simple argument. Now, this is a curve, so a little piece of a curve has a notion of length. And so I can talk about, for example, how much snow per unit length on the driveway multiplied by each little length, and that tells me how much snow is on each little piece. And I then add that up over the entire curve. Let me rephrase that. I hope to be able to add that up over the entire curve. And how are we actually going to turn the crank on this? How are we actually going to compute this? Yeah, we'll get to that in a minute, right? But just conceptually, the plan is I would like to be able to add up over the entire curve a bunch of little pieces, and on each little piece, mass per unit length times length. Simple as that. Okay. All right. So with this strategy, just remember that this thing that's eventually going to be our integrand, remember that is always some sort of a density. It's always whatever your accumulating quantity it might happen to be. If it's snow, okay. If whatever it might happen to be, that integrand means stuff per unit length, stuff per unit size, to put it more generally, which is what a density is. Okay. All right. So it's going to turn out it's actually not that hard to compute these things. We'll get to those details in a minute, but the notation is this. I think this is pretty believable notation in the following hopefully familiar senses. Right? Pretty natural. Pretty. You might even say expected, right? Kind of notation. And the terminology now is a little strange. This is called a scalar line integral. Let's talk about the line integral part of it. Well, let's talk about the integral part of it. Well, it's an integral because it's a Riemann sum. Of course, it's an integral. That's kind of the easy part of the terminology. Why do we call this a line integral? This is a little bit weird. The word line doesn't, in all contexts, mean a straight line. Right? it. Sometimes line means curve. Right, so I think arguably case could be made this would be more naturally described. This would be more naturally described as a curve integral. But that's just not the term that's persisted. Some people, I appreciate, will refer to this as a path integral. That's a common-ish term, but frankly, line integral is more common. Okay. All right, so the line part of the terminology is a reference to the nature of the domain. Here's the really not obvious part. Why do we call this a scalar line integral? Very not obvious. You won't be able to see this coming. The reason we call this a scalar line integral is it turns out there is another, I think, importantly different kind of line integral. Very naturally, we're going to want to call it a line integral, but it's importantly different from this construction that we have here. And one of the distinguishing features we're going to find is that in this one, the differential and the integrand are both scalars. Most naturally. So thus the term scalar line integral. So believe it or not, this other one that we're going to talk about next week, vectors, not scalars. It's weird. It arises pretty naturally, as it turns out. But anyway, it's definitely a different construction. Okay, so we have to call this a scalar line integral to avoid confusion. Okay, last thing real quick, let's talk about how to compute these. It's actually pretty straightforward. Remember, with change of variables, when you have an undesirable domain, and now let's take a quick moment to acknowledge this is a pretty undesirable domain because I don't even know how to get started. Right? What am I supposed to do? Am I supposed to do a double integral here? There's no area. I can't do a double integral. Right? Am I supposed to do a Calc 1 style integral? We didn't see anything in Calc 1 that addressed the fact that this domain is curved, right? How do you account for the way it curves? That single variable integral right off the bat doesn't seem like that's a candidate either. So undesirable domain. And the big idea from change of variables, when you have an undesirable domain, view it as an image of something. In this case, I'm going to view it as an image of an interval on the t-axis. And good news, we already know how to do that. It's called parametrizing, right? Flashbacks to early chapter 1. We talked about section 1.2, I guess it was. We talked a lot about how to parameterize curves. That's exactly the tool that we need here. This undesirable domain then is an image, and then I do a pullback. Details to follow in a moment. This undesirable integral on an undesirable domain, I will pull back through the parameterization to result in a single variable integral on an interval on the t-axis, Calc 1, plug and chug, that y'all are all experts at. So that's going to be the really nice punchline, and this is a pretty good place to draw the line. We'll draw the line right there. See y'all on Friday. Good luck studying for the test. See you then.